Hello everybody, hope you're having a wonderful day and welcome to Maths for Fun. Today we're going to be talking about all the numbers. Yes, all the numbers. We're going to be looking at all the different types of numbers there are and trying to classify numbers. Just like we can classify life on earth, vertebrates, invertebrates, mammals, there are in fact ways to classify numbers which are quite useful for mathematicians. We're going to be taking a look at this. Number 5 already did a video similar to this over on their channel, kind of inspired this video. That's why this video is in a very number file type of style, but the classification system they used was in terms of computable numbers, constructible numbers, transcendental numbers, which is a very useful classification system, and I encourage you to go watch the video. But the one we're going to be doing today is slightly more mainstream, the one you might use at school, and the one which I think mathematicians use a bit more. So let's get started. So the first type of number we're going to talk about is natural numbers. So natural numbers are basically 1, 2, 3, 4 and on and on and on to infinity, right? So these are basically the numbers you would deal with every day. These are the first kind of numbers, before decimals and fractions and all that stuff came in. These are the natural numbers, right? So we can think of these are counting numbers. You can have 5 rocks, 40 bags of flour, 3 oranges, so on and so forth. So 1's a natural number, 55 is a natural number, 4038 is a natural number, 5 is a natural number, and so on and so forth, right? So basically natural numbers are all positive whole numbers, 1, 5, and no matter how big they get, 1 million, also a natural number, numbers that you can count out. And as I said, these are sort of the first type of numbers that came around. That's why they're called natural numbers. Now one important note is that I said positive whole numbers, and that's because 0 is not a part of the natural numbers. So 0 is not a natural number, right? And that's going to come up later. So 0 is not a natural number. But aside from that, all the positive whole numbers are indeed natural numbers. So what I'm going to do is that I'm going to get a little diagram going over here so we can see how all the different types of numbers link together. So I'll do like a Venn diagram. For the first one, I'm going to write natural numbers. Going to write a definition, and let's draw a circle around that. Great. And the more types of numbers we add, the more it will become clear what that diagram means. Okay, so we talked about natural numbers, right? Let's move on to the next type of numbers. So next type of numbers are whole numbers. Now whole numbers has got a different colloquial use, numbers which aren't fractions, numbers which are whole in nature, but the technical mathematical definition is as follows. So whole numbers go 0, 1, 2, 3 and on till infinity. So as you can see, these whole numbers are really quite similar to the natural numbers, right? Only difference being 0 is included in the whole numbers and 0 is not included in the natural numbers, right? So the only difference between whole numbers and natural numbers is whole numbers include 0 and natural numbers don't. So as you might imagine as well, you can just see that all natural numbers are also whole numbers, right? Because you got 3 here, 3 here, 2 here, 2 here, and indeed all the natural numbers do also count as whole numbers. It's kind of like how all thumbs are fingers, but not all fingers are thumbs, right? So once again, the only difference between whole numbers and natural numbers is that whole numbers have 0 included and natural numbers don't. So now going back to our diagram, I'm going to write whole numbers next. Right, and I'll write the definition here. And what I'm going to do is in this outer ring, I'm going to write the exceptions, things that aren't natural numbers but are whole numbers. In this case, it's only 0, but as we do more and more, you'll see how that works. It's basically like a Venn diagram. So once again, all natural numbers are whole numbers, and 0 is the whole number that's not natural. Okay, so we've talked about natural numbers, whole numbers. Let's move on to the third type of number. That is integers. Must be recalling your middle school maths. So integers are really interesting. So if I were to list out all the integers, right, I would go something like this. So I'd start from negative infinity, then dot dot dot, -2, -1, 0, 1, 2, dot dot dot, all the way till positive infinity. Now that's a bit, now all this basically means is we are opening the door to negative numbers, right? So all the positive and negative whole numbers. I know I defined it earlier, but I'm using the colloquial use now. So all the positive and negative whole numbers. So we sort of open the door towards negative numbers. Let's look at a few examples and hopefully it will make sense. So as you might imagine, 2 is also an integer, right? But the new ones which come are -3 is an integer, -43 is an integer, 5 is also an integer, 7 is also an integer, right? So we've got all the positive whole numbers, but now also all the negative whole numbers, and of course 0 is also included, right? Now there's no fractions, no decimals, no funny stuff like that, just all the positive whole numbers and all the negative whole numbers, right? So -3, -43, -1,000,000, also an integer, right? So go back to our diagram here. We should be drawing it better. We can now move on to integers. Write a shortened definition here. And once again, we're going to write all the exceptions in the outer ring. So these are just all the negative numbers. So -3, -5, -6, -43, -109, and so on and so forth, right? So hopefully the diagram is starting to come together and you can see what integers really are. Basically all the positive whole numbers and all the negative whole numbers. Once again, decimals, fractions, they don't count as any of these. And once again, you can see through the diagram, all natural numbers are whole numbers and all whole numbers are also integers. Hopefully that's making clear, right? So we're going for the most constricted version to the more general versions. Alright, so we've talked about so far natural numbers, we've talked about whole numbers, we've talked about integers. Let's move on to another very interesting type of numbers, and those are rational numbers. So let's talk about rational numbers. Now rational numbers get their name from the word ratio, right? So they're not numbers that are logical or not Trump supporters, they're rational numbers because of the word ratio. Why ratio? Rational numbers are basically any number which you can represent as a ratio, specifically a ratio of two integers. So the textbook math definition for what rational numbers are is as follows. So basically you've got x is a rational number if it can be represented in the form p upon q, where both p and q are integers. This z means integers and this curly e means that they are. So basically this entire thing is saying that both p and q are integers and q is not equal to 0. So this is a long overdraft complicated way of saying fractions, right? So rational numbers are fractions, but more specifically they're fractions given that both the numerator and denominator are integers. Remember, positive and negative whole numbers, so the numerator and denominator integers, and that the denominator is not 0, because remember, if the denominator is 0, you can't divide by 0, it becomes undefined. So once again, rational numbers are just any number which you can write as a fraction of two integers. So let's look at some examples. This basically opens the door to all sorts of fractions, right? So instead of being limited to boring 1 or 5 or -6, right, I can have now 2 upon 3, 5 upon 4, 23 by 7, 121 by 343, it doesn't matter, right? I can even have negative fractions, -5 upon 7, -3 divided by 121, and so on and so forth, right? Any two integers in a fraction, that's a rational number, right? So you can so as you might imagine, this opens the door to fraction, and all fractions like this are indeed rational numbers. But rational numbers can be written as fractions and also as decimals. So you might remember from your grade school that you can convert between fractions and decimals. That's indeed the case. So rational numbers are not only represented as fractions, but a lot of decimals are also rational numbers. But here's the thing, not all decimals are rational numbers, right? So not all decimals can be written as a fraction, right? So while a lot of decimals are rational numbers, not all decimals are rational numbers. So we have a couple of rules, right, or a couple of conditions to check if a decimal is a rational number, if it can be written as a fraction. Let's take a look at those. Alright, so the first type of condition is terminating decimals, right? Terminating decimals. Now what does terminating decimals means? It's basically if a decimal terminates, I know it's a rational number. Now what does that word terminating mean? Well, let's take an example. Let's say I've got 5.5, and that's it. If a decimal has a finite number of decimal places, right, a finite number of decimal places, it is a rational number, straight, period, right? So in this case I've only got one decimal place, this is indeed a rational number, and in fact it can be written as 11/2 just to prove it, right? And as long as the decimals don't go on to infinity, as long as they end at a given point, there's a finite number of decimals, period, it's a rational number. Let's look at another one. 3.125. Even though there's 3 here, as long as it ends, it is indeed a rational number. And if I just grab my calculator here and quickly check what that is equal to, 25/8. So, and this I've used 1 or 3, but even if a decimal is 40,000 digits long, as long as it ends at a given spot, as long as it terminates, it is 100% a rational number. So most of the decimals we deal with in real life tend to be rational numbers because they don't go on to infinity, they end at a given point, right? This is condition number 1. If a decimal ends, right, it terminates, 100% rational number, right? Now let's look at scenario number 2. And this is the thing that some decimals, the decimal places go on to infinity, but even some of those decimals, the ones that they go on to infinity, are also rational numbers. So just because the decimal does not terminate doesn't necessarily mean it's not rational. So let's look at the second condition. So second condition are recurring decimals. Let's have a look at what these are. So let's take a simple example. Let's say I've got 3.3333 and ongoing, right? So these decimal places go on forever, right? They don't stop, they keep on going till forever. But as long as there is a discernible, consistent pattern in the decimal places, right? As long as there is a consistent pattern in what the decimal places are, if there is a recurring pattern in the decimal places which go on to infinity, it's a rational number, right? So in this case, I've got 3.3333. 3 just keeps on repeating, right? It's a recurring pattern. So I can say with confidence that even though this goes on to infinity, because there is a recurring pattern in the decimals, it is 100% a rational number, and this is a rational number. And as you can see, this is just equal to 10/3, right? And this pattern does not necessarily have to be only 1 digit long. If you've got 7.161616 and ongoing, or 3.125 and ongoing, both of these are also rational numbers, right? So the pattern does not only have to be 1 decimal place long, it can be 5,000 decimal places long. As long as it repeats consistently, it is 100% a rational number. Now for those of you who are very interested like why this is the case, I'll give you a little tidbit. Of course you can prove it mathematically, but one interesting way I like to think about it is that the fact that these decimals are recurring have nothing to do with the decimals intrinsically or mathematically. There's nothing about 1/3 that makes it mathematically recurring. It's just a consequence of the fact that we use a base 10 number system. So that's just something for the more perceptive of you to think about. But my point being, overall, as long as you can find a discernible pattern which repeats till infinity, even if the decimals go on to infinity, it is a rational number. So that was a lot of information. Let's just recap. Rational numbers are any number which you can write as a fraction between two integers. So that of course includes all the fractions you might be familiar with, even negative ones, right? And a lot of decimals are also rational numbers, but not all of them. So decimal is a rational number if it ends, if it terminates, right? If it's got a finite number of decimal places, or if it goes until infinity, as long as it's got a consistent repeating pattern in those decimal places, it's what we call a recurring decimal, it's also a rational number. So hopefully that clears that up. So if we could go back to a little diagram here, I can write down rational numbers, write on a shortened definition here for space readings, and let's give it a big old circle. And once again, we would write all the exceptions here. So all the numbers which are rational numbers but not integers, and all the rest, right? So this includes all the fractions. So let's just go crazy. 2/3, 5/4, 23/48, right? -4/7, -3/2, 42/3, and so on and so forth. Let's also include some decimals. So 3.1256, -7.159, -3.33 ongoing, and so on and so forth, right? So hopefully this gives you a better idea of what rational numbers are. right? And now that we've discussed what rational numbers are, it brings us to a very interesting place, right? Because now we get to talk about a very, very interesting type of number, and those are irrational numbers. So, irrational numbers are basically just the opposite of rational numbers, right? That's why, hence the name irrational. They're the opposite of rational numbers, and they've caused quite a few problems in mathematics in the past, but are now a very integral part of it. So, let's have a look at what they are. So, irrational numbers, as I said, are just the opposite of rational numbers. So it is literally any real number which you can't represent in the form p upon q, where p and q are both integers. You know the drill. The q is not equal to 0. So any real number which you can't represent in the form and as a fraction of two integers, any real number which you can't write as an integer, that is an irrational number, right? So you might think, are there any numbers which you can't write as an integer? And indeed there are. So let's look at some examples. So the square root of 2 might ring a bell, right? So the square root of 2 is basically a number which you have to multiply by itself to get to, right? And while this does have value, you can't write it as a fraction. It's not possible. Square root of 2 cannot be written as a fraction of two integers. Try your best. It's not possible, right? So just not. And in fact, back in the Greek days, this was the first number that was proven to be irrational, right? And the guy who proved it to be irrational was actually executed because he destroyed the whole mathematical belief of a group called Pythagoreans. So point being, square root of 2 is irrational because you can't write it as a fraction. Very interesting type of number. Let's look at a few others. So another famous example is pi. Now there was a very big misnomer in the mathematical education that was there about 10 years ago, right? And that was that pi is in fact equal to 22/7. This is a big misnomer that's there. Cannot be further from the truth. 22/7 is a good approximation for pi. It's correct to about 2 decimal places, but pi is far from equal to 22/7. Right? Pi is not equal to 22/7, and in fact pi cannot be represented as a fraction at all, period. It's not possible, right? Another famous one is Euler's number, E, very almost synonymous with instantaneous interest or growth, because it is its own derivative. So when you want to talk about compound interest, growth, right, you use E. When you want to talk about sort of instantaneous interest, that was where it originally came from. You use E, and it too is an irrational number. You can't write it as a fraction. It's not possible. So another famous example is phi, the golden ratio, right? This is one that gives rise to all sorts of cool logarithmic spirals. One which is said to be found in the one which is very closely linked to the Fibonacci sequence, one that is said to be found in the seed arrangement of flowers, and one that is often been touted as the most irrational number as well, right? So point being, all of these are numbers which you can't write as a fraction, and that's why I've been writing them as symbols and not numbers, right? Because you can't write them as a fraction. But interesting enough, what you can do is you can write these numbers as decimals. So you can write irrational numbers as decimals, but when you try to write them as decimals, there's a very, very interesting thing that happens. So let's have a look. So when you try to write a irrational numbers out of the decimal, its decimals go on till infinity. That means it never terminates, never ends. They keep on going till infinity, and there is no discernible pattern. You can check 40,000, 1 million digits, you will not find a pattern that recurs. No consistent recurring pattern at all. Let's take pi in as example. So pi is equal to 3.14159262654 and ongoing. As you can see, it goes on till infinity, and just from this part here, no discernible pattern. You could check 40,000, 1,000 digits, right? Look it up on the internet. You will not find a single pattern. It is no pattern, and it goes on till infinity. That's true for square root of 2, that's true for E, that's true for phi, right? Which is the golden ratio. None of these numbers, when you write them as decimals, will have a recurring pattern, and their decimal places will go on to infinity, right? These are irrational numbers. Hopefully they piqued your interest. So far the way we've been drawing this diagram is getting more and more general. So all natural numbers are whole numbers, or whole numbers are integers, or integers are rational numbers. But it wouldn't really make sense if all rational numbers were irrational numbers. So irrational numbers are actually going to be their own blob on the side here. They're a completely different type of number from all of these, right? So rational numbers are one type, and irrational numbers are the other type. They're completely different. right? It's not another big circle. So we're going to write down irrational numbers. I think I'll just leave it at that. I'm going to write down a shortened definition here, and same examples I gave you guys earlier. Great. So irrational numbers, rational numbers. We've come quite a long way. And now we get to talking. Now we're quite close to the end. Now we get to talking about real numbers. Now real numbers are nothing special. It's basically just the combination of all the rational and irrational numbers. Literally, just rational and irrational put together. All of them, whatever you're left with, are the real numbers, right? And these are numbers which everyone except a career mathematician would work with, right? So 2 is a real number, minus 5 is a real number, 4.9 is a real number, pi is a real number, square root 2 is a real number, right? All the rational and irrational numbers put together, they're all real numbers. So it's actually a pretty neat way to think about what a real number is. I need some more paper. Actually, no, I can do it here. So the way I like to think about real numbers is if that number exists on the number line, the one you learn in school, it's a real number straight away, right? So 1, there you go, that's 1 on the number line. So definitely a real number. 1 upon 3, fraction, that also exists on the number line, somewhere around there. So it's also a real number. Pi, even pi, somewhere around there in the number line, it exists on the number line, right? And once again, it's a real number, right? And any number which you can place or which exists on this number line is a real number, hands down, right? So go back to my diagram here. One big circle is coming up. And write down real numbers. And honestly, as I said, real numbers are just a collection of rational and irrational numbers. There's nothing which comes here, right? There's nothing that's a real number and not irrational or irrational numbers. All real numbers are either rational or irrational, right? So there's nothing that comes here. And this is a collection of pretty much all the numbers, though we're not done, right? So these are all the numbers which like anyone except a career mathematician would deal with, right? And you might be thinking to yourself, are there any numbers which you can't put on a number line? I sure can't think of any. And I guarantee most of you watching this video, you can't think of a number that's not a real number. In fact, as I said, this is the kind of numbers we deal with every day. And in fact, about maybe 500, 600 years ago, these were all the types of numbers that existed, right? There were no other types of numbers. There was nothing beyond real numbers. This is it, right? But a very, very, very interesting development happened around 1600, 1700 in mathematics, which changed it forever. And that was the introduction of imaginary numbers, completely new, different type of number which no one really thought of before. So let's have a look at what those numbers are. So I'll be needing a new piece of paper for this. So let's say I take a positive number and I multiply it by another positive number. What's the answer going to be? Positive, right? Positive times positive. 2 times 4 is 6. 3 times 2 is 2 times 4 is 8. 3 times 2 is 6, right? Any positive number times any other positive number will always give you positive number. Okay. What if I take a negative number and multiply it by another negative number? What's the answer going to be? Well, in fact, still positive, right? Negative times negative makes positive. So 2 times 3 is 6, but minus 2 times minus 3 is also 6, right? So any positive number times any positive number is a positive number. Any negative number times any negative number is a positive number, right? So that raises the question, what would the square root of a negative number be? So for those of you who need a refresher, square root is basically a number which you multiply by itself to get that number. So square root of 4 is 2 because 2 into 2 is 4. Square root of 81 is 9 because 9 into 9 is 81, and so on and so forth. But the interesting thing is we just proved that any positive number times any positive number is a positive number, and any negative number times any negative number is a positive number. So this just does not seem to exist. Let's take an example to exemplify what I'm trying to say. So let's take the square root of minus 9, right? So well, it's not 3, right? Because 3 into 3 is 9. But it's also not minus 3, because minus 3 into minus 3 is also 9, right? And in fact, you can look all you want on the real number line, you won't find a single number which when you multiply it by itself will give you 9, because we just proved if it's positive, its square will be positive. It's negative, its square will be negative. And if it's 0, 0 squared is just 0, right? So there is no number on the real number line which can give you the square root of a negative number. It just does not exist, right? So for a long time, this was just like this concept, square root of a negative number, does not exist. But it turns out that having the square root of a negative number is very, very useful to mathematicians for a variety of different ways. It's very, very useful to have a square root of a negative number in maths. So about 500 years ago, what we did was we just made one up. We said that the square root of minus 1 is some number I for imaginary number, right? So we said that the square root of minus 1 was I, and we call that the imaginary number, right? And this was because it was very useful to us, and this is a completely different type of number. It just does not exist on the number line. You can't put, no matter how hard you try, you can't put I on the number line, right? It's a completely different type of number altogether, right? And this defining characteristic being that when you square it, you get minus 1, right? This is what defines I right here. And once again, we didn't do this for no reason. We did it because it was very useful to us, and this opens the door to imaginary numbers. So of course I is an imaginary number, but not just I. 2i, 2 times I is also an imaginary number. 5i is also an imaginary number. Minus 7i is also an imaginary number. 10i is also an imaginary number. So basically, if you can give I a coefficient, you can multiply it by something, right? And that's also an imaginary number. Like minus 2i is not a real number, right? Because it's got I in it. So this opens the door to these imaginary numbers, right? So basically, think about it like I and any coefficient with I. So 2i, 5i, minus 7i, 1 million I, these are all imaginary numbers, right? And these are completely separate from the real numbers. So what I'm going to do is, I already kind of filled up that diagram here of all the real numbers, right? So I'm going to start a new diagram, short one, just to exemplify what I'm talking about. So let's say this is the real numbers. Just write some examples. 1 minus 9 by 4 upon 3, so on and so forth, right? And let's say this is the imaginary numbers. Let's give it I, minus 2i, 4i, 3i, 40i, anything, right? So these are the imaginary numbers, right? So real numbers, imaginary numbers, completely different, no overlap, completely different types of numbers. These ones are real, we use them every day, they're on the number line. These ones are imaginary. No one but a career mathematician will use them on a daily basis. They're weird, mystical, or don't even define quantities. We think of numbers as defining quantities. 5 gallons of milk. Even you could have someone who's 5 meters tall, technically speaking, right? But imaginary numbers, not that. And the name imaginary might lead you to believe that these numbers are somehow fake. No, believe me, these exist. These numbers do exist. They're very integral to mathematics, right? We just call them imaginary numbers because that's where the origin came from. So these numbers aren't fake, all right? Just so, because that's a common misnomer. And finally, we can come to the last type of number, and those are complex numbers. Now, complex numbers are nothing special, right? They are just the union of a real number and an imaginary number, right? So you take a real number and an imaginary number and you put them together, you get complex number. We call them complex because they're not simple, they've got two different components. So let me give you an example of a complex number. So 1 plus 2i, this is a complex number, right? And it might look like it's two numbers just added together, but no, it's one number which has two parts, a real part and an imaginary part, right? And the reason we don't just add these two together into one number is because we can't. Two fundamentally different types of numbers, I can't even add them together, right? It's not possible. So we are forced to represent it as the real part plus the imaginary part. But this entire thing is one number, and that is a complex number, right? The real part, imaginary part. And 1 plus 5i is also a complex number. 32 plus 6i is also a complex number, right? Minus 32 minus 5i is also a complex number. And in general, we mathematicians say any number which you can represent in the form a plus bi, right, is a complex number. Any number which can be written like this, and a and b can be any, any real number, anything, pi, 0, minus 3.2, anything. And one interesting fact you can see is that, well, according to this, I could also have 1 plus 0i, which is just equal to 1. And that's true. 1 is a complex number. 5 is a complex number. Pi is a complex number. E is a complex number. 3 over 2 is a complex number. I is a complex number, right? But this is, so everything is a complex number, right? Technically speaking. But when mathematicians say complex numbers, they're usually talking about complex numbers which aren't real numbers, right? So while 1, 5, 6, they're all technically speaking complex numbers, right? Because you can say plus 0i. When mathematicians, when we say complex numbers, we are usually referring to all the complex numbers that aren't real numbers, so all the complex numbers that are not real numbers. 5 plus 3i, 2 plus 1i, and so on and so forth. So now what I can finally do is complete the diagram. One big blob right here. We call that complex numbers. And I'll add all the complex numbers in. So 3 plus 5i, 7 plus 6i, 4 plus 9i, 9 plus 3i, what else is there? Minus 7 minus 5i, e minus pi I also exists, right? And so on and so forth. So as you can see, complex numbers. So let's go backwards and just summarize everything. Biggest type of numbers, complex numbers, right? Any number which has real part and imaginary part, right? Now you subdivide them, you've got complex numbers which are a union of the two, but you can also have individual complex numbers. You can have a real number, right? 1, any number which you can put in the number line, 1, 5, pi, minus 2, right? And you can have an imaginary number only in terms of I, right? Which is the square root of a negative number, right? So complex number you can divide into these two places, real number or imaginary number or combination of the two, right? This is, now let's take a closer look at real numbers. Real numbers can be divided into rational and irrational numbers. Rational numbers are ones which can be written as a fraction. Irrational numbers are ones that can't. Now, amongst the irrational numbers, ones which are whole numbers, positive or negative whole numbers, like minus 5, 4, 3, 2, all these ones which aren't fractional or decimals, whole numbers but are positive or negative, these are integers, right? These are integers, okay? And as you can, now amongst the integers, all the counting 0, all the positive integers, right? 1, 2, 3, 4, 5 till infinity, including 0, those count as whole numbers. And if we just include 0 and we only talk about the positive integers, 1, 2, 3, 4, and on and on, we get natural numbers. And that's all that there is to it. So these are all the different types of numbers, at least to my knowledge, I mean, like, unless you're doing an undergraduate degree in advanced mathematics, these are all the numbers you're going to need to know. Of course, there are more. You got ordinals, and I'm not sure if ordinals count as a new type of number, but they're very, very different. Transfinite algebra also comes, and maths has no lack of complexity in it. But point being, these are the broad types of numbers, even for a mathematician, right? And hopefully, I was able to exemplify what each one means to you in this video. I hope you learned something interesting. Hopefully you took something away. Please, after this video, go watch the number 5 video. It's the same numbers we're talking about here, just a new way to think about them. And yeah, I hope you learned something. Please let me know what you think in the comments. Let me know if you got some feedback, a compliment, or you think I got something wrong, anything. I appreciate your feedback. Please write in the comments. And that being said, I hope you have a wonderful day ahead. Thank you for watching.